All right, good morning, happy Wednesday, and April Fool's Day. So, what we are going to do in this recording is we are going to go through page 1 and page 2 of our chapter 6, section 1 guided notes. Now, just as a reminder, you guys just passed in your Get Salty mini posters. That was about chapter 5. In chapter 5, we were looking at everything about ions and ionic compounds. We did those self-made guided notes. You guys have listened to some audio recordings of me. And just as a reminder, the big idea about ionic compounds is we have a cation and an anion coming together. We have a full positive charge and a full negative charge coming together. Here in chapter 6, what we're going to start looking at is a different type of bond, a covalent bond. You've probably heard about this before from middle school. But what we're going to talk about is about how different these are when we compare them to ionic. So although we are moving into a new chapter, we are definitely going to keep talking about ionic bonds. They are kind of what we're going to compare our covalent bonds to. So I will be going through page 1 and 2 today on Monday. So again, we're doing the Monday-Wednesday schedule. So being that today is Wednesday, you will hear from me again on Monday. So on Monday, we're going to keep doing these guided notes. I'm going to do pages 3 and 4, and then we'll talk about some practice work that goes along with those pages about electronegativity. And my plan as well is we do have a weird chapter 6, section 1.5 guided notes to do as well. So not only do we have covalent, not only do we have ionic, but we also have metallic bonds that we're going to be looking at. Now, with metallic bonds, your textbook does not do a fabulous job. They give you about one paragraph about metallic notes. So I will have some guided notes for you. We'll do it after covalent. But just as a heads up, if anybody likes to go ahead of the notes, that is where we're going. So for these guided notes, let's get started. Just a reminder of our vocab and our objectives. We've got a ton of vocab terms here. Not all of them are going to be seen today, but covalent bond, molecular orbital, bond length, bond energy, non-polar covalent bond, polar covalent bond, and this thing called a dipole. Our objectives, we have 4 of them. Explain the role and location of electrons in a covalent bond. We're going to have a specific word for that. Number 2, describe the change in energy and stability that takes place as covalent bonds form. So we'll have a graph that we'll look at, and we'll talk about why does it form a bond. Number 3, distinguish between nonpolar and polar covalent. And number 4, compare the physical properties of substances that have different bond types and relate those bond types to electronegativity. So those objectives 3 and 4, we are going to see that on Monday. We're going to talk about 1 and 2 today. All right, getting ready, started here in our guided notes. In ionic compounds, electrons are blank from one another to gain noble gas configurations. So we had said that in ionic compounds, electrons are transferred. So your first blank in your guided notes, that is transferred. Now, we like to use the word transferred with ionic compounds because when you were getting your Get Salty posters, for example, if you had done sodium chloride, you recognize it is one electron that sodium has lost, and it is the same one electron that chlorine has gained. It's that positive one and that negative one coming together. So that's why we say transferred, and that is the word that I will use over and over and over again. So you could think about ionic bonds as giving up an electron, as maybe we could say having an electron be stolen. All of those things that describe the movement of one electron. This is going to be different because in covalent compounds, this is our next blank, in covalent compounds, electrons are shared. In covalent compounds, electrons are shared. So please take down in these blanks here in covalent compounds, you'll notice you have 2 blanks. You can probably fit electrons are shared at the top. And I have one more thing. In covalent compounds, electrons are shared, just like you may experience with your brothers or sisters. Things can be shared evenly or unevenly. So that's going to be about looking at those vocab terms, a polar covalent versus a non-polar covalent, where one is shared unevenly and one shared evenly. So please also take note, not only in covalent compounds are electrons shared, they can be shared equally and unequally. So if we think about this just real quick, I like to say like potato chips. If you're sharing a bag of potato chips, you can be very nice and share one potato chip with your brother or sister. For every potato chip you have, you split it right down the middle, 50-50. Or you can be a little bit of a brat and you can say, yeah, I'll share my potato chips with you, and give them one tiny potato chip and eat the bag, the rest of the bag to yourself. Again, it is technically sharing. You're just not sharing very fairly. So we'll talk about that with covalent compounds too, where some of them share, they just don't do a very good job at sharing. All right, our definition for a covalent bond, our next blank here. A covalent bond is a bond formed when atoms share one or more pairs of electrons. A covalent bond is a bond formed when atoms share one or more pairs of electrons. So it's super important that you guys take down not only is a covalent bond when atoms share, but when they are sharing one or more pairs of electrons. We're going to talk about these pairs of electrons, and they're always going to be sort of paired up in twos. We can also identify a covalent compound as a nonmetal plus a nonmetal. We can also identify a covalent compound as a nonmetal plus a nonmetal. So again, just as a reminder with ionic, we said an ionic was a metal plus a nonmetal. So here's a different combination. We have a nonmetal plus a nonmetal. So that's everything over on the right-hand side of your periodic table, those nonmetals, halogens, noble gases. Any combination of those would be some covalent compound. We will get the third combination, which will be a metal and a metal, but we'll talk about those metallic compounds, those metallic bonds, in a couple of days. Moving right along here, we have another vocab term, a molecular orbital. So molecular orbitals are super, super similar to atomic orbitals. Atomic orbitals, those S, P, D, and F, spherical, dumbbell-shaped, or we could also say hourglass-shaped, weird and weirder shaped orbitals. Those were just for an atom. Now that we have two atoms making a bond together, we can talk about how the location of an electron is going to change. So your definition, a molecular orbital is a region of high probability that describes where an electron is likely to be found when it participates in covalent bonding. A molecular orbital, a region of high probability that describes where an electron is likely to be found when it participates in covalent bonding. And I remind myself right underneath that, aka shared between two nonmetal atoms. So the big idea here is that if an atom by itself, an S-shaped orbital of an atom, anywhere within that S-shaped orbital, an electron is likely to be found. That's its described probability. If you have an electron that's shared between two atoms, the probability that it's going to be found between the two atoms rather than maybe off to the left or over in, far away. I don't know how to describe this without having a visual image. But if you have the electron likely being participating between those two atoms, that just means that's where it's going to be found at a greater probability, and that's why we're describing it as a molecular orbital rather than an atomic orbital. There are also names for molecular orbitals. If you want to write them down, you certainly can, but don't worry about them. We're not going to worry about them in this class. I just need you to understand that the probability where the electron's going to be, it's going to be more likely to be found in between the two atoms where that bond is. All right, moving right along here, we have a little bit about energy and stability. We are still talking about the stability of a complete octet. In ionic compounds, we got a complete octet, or that completed energy level, by gaining or losing electrons. Again, that's why we talked about ionic compounds as fully transferring electrons, because they fully gain them or they fully give them up. In covalent compounds, because the electrons are going to be shared in pairs, we are still going to be able to get to like a completed octet, but it's not going to be through transferring of electrons. It's going to be that two of these atoms feel sort of the sharing or the completed of their energy level with each other. So they kind of complete each other. So looking at these bullet points here, Besides the noble gases, most atoms have low stability and have a greater stability if part of a compound. So we've talked about this. Our lone elements, thinking about our halogens, for example, they're super reactive as singular atoms. They really want to form their elemental form. They're super reactive. So too with most things on the periodic table. Besides the noble gases, they want to do this action. They want to form a bond. And again, we'll talk about the reason why, because again, these aren't emoting. Sorry, there's a dog barking outside my window. So the reason why we are so distracting. I think I gathered myself. The big idea, the whole thing that I'm trying to say here, I'm getting distracted by a dog. But the reason why this happens, again, atoms don't have like emotions, that kind of thing. It's because they're going to a lower energy level. And because those lower energy levels are the easiest thing to do, it persists. That's what we see. I should keep it at that. All right, so second bullet point. When two or more atoms share electrons, they both receive the stabilizing effect of gaining electrons in their outer energy levels. A good example for this is hydrogen. You have a nice image in your textbook about this. Moving right along here, the potential energy curve illustrates this. Oh, so good. We are going to go a little bit deeper into our hydrogens. The image in your textbook, you have this graph. You also have, if you notice these two spherical hydrogen atoms on this graph, you also have like an electron cloud image that shows that bond on your textbook. So I would encourage you to look at that. All right, so the attractive force of one nucleus pulls the electron cloud of some other atom towards it. And so we're going to talk about all of the different points on this graph, but that's what these bullet points are describing. So as the atoms get closer to each other, they reach this lowest potential energy. That is going to be the lowest point on this graph. If the atoms are too close to each other, which is sort of this first point, I wish these were labeled A, B, C, and D. Anyways, so if they get too close to each other, the nuclei sort of repel against each other. So we'll define bond length in just a second, but I just wanted to say one more thing about this graph. So what this graph is representing is sort of the 4 stages of when bonds form. So the first stage is the one that's farthest to the right, those 2 hydrogen atoms that are far away from each other. It says R is equal to 300. So this is talking about like the bond radius. So if these atoms are far away from each other, what we'll notice is they are unstable. They kind of see each other from around the other side of the room. And as they approach each other, the positive nucleus of one atom is attracted to the valence electrons of a nearby atom and vice versa. So each nucleus is attracting a valence electron of a nearby atom. We know electrons are negatively charged, nuclei are positively charged, so that's why they are pulling each other closer. As we move a little bit more to the left, where those 2 hydrogen atoms have started to touch, but we haven't gotten to the very dip on our graph. Here now they are getting closer. They're lowering their potential energy, but what we'll notice is they're just a little bit too far away. They really want to get to that, we could even call it a Goldilocks zone. So moving over to the left once more, this is that Goldilocks zone. The deepest part of this graph, it is at the lowest potential energy. This is where those bond lengths are going to be measured. Now, we'll say something about these bond lengths in that they're in constant motion. I am about to run out of time here too. So that's what it is. I think I have another minute, and I'll put the rest in another recording if I have to. But so these 2 hydrogen atoms, they get to this Goldilocks zone together and they still are wiggling back and forth. So I want you guys still to envision that these atoms, they are composed of these valence electrons. And again, when we think about an atom, what we're really thinking about is our nuclei, right? That's that football on a football field. The entire football stadium is our atom, and all of that space in that football stadium is the electron cloud where these electrons are located. So as these atoms are coming closer and closer to each other, they're overlapping. Those orbitals overlap. That's where the molecular orbital is, that perfect sort of Goldilocks zone between the valence electrons and the nuclei. And then if they get too close, then those 2 positive nuclei, this is the most left position on this image where the 2 hydrogen atoms have an R of 45, or these 2 atoms get so close together, they're too close, and the nuclei repel against each other and they come back to that Goldilocks zone. So what we'll talk about with bond length with this misconception too is about, I want you to understand that we're trying to use models to represent bonds, but every model is flawed. So